Hello everyone, my name is Shobhita Paul. I'm from Assam Don Bosco University and today I'm going to talk about optical amplifiers. So at the beginning we'll know why do we need these optical amplifiers. So when a signal is transmitted in a transmission line over long distances of 100 km, after a certain distance the signal gets attenuated at large extent, so it's very difficult to restore the signal at the receiver end. Earlier, regenerators were used to transmit these signals, where these optical signals are converted into electrical signal and the electrical signals are converted into optical signal at the receiver end. In this way, the signals get cleaned, amplified and retransmitted. So they used to have some disadvantage like bitrate dependency, modulation format dependency. But in optical amplifiers, they are totally independent of these disadvantages. So what is an optical amplifier? An optical amplifier is a device that amplifies an optical signal directly without the need to first convert it into an electrical signal. An optical amplifier may be thought of as a laser without an optical cavity, or one in which feedback from the cavity is suppressed. So in this figure we can see that the optical signal is directly transmitted through the optical amplifier medium to the receiver end. So let's talk about the types of optical amplifiers. The first one is SOS. It stands for Semiconductor Optical Amplifier, which are the amplifiers which use a semiconductor to provide the gain medium. The second one is EDFA, which stands for Erbium Doped Fiber Amplifier, which is an optical repeater device that is utilized to boost the intensity of optical signals being carried through a fiber optic communication system. And the last one is Raman amplifier. Here the signal is intensified by Raman amplification. Unlike the EDFA and SOA, the amplification effect is achieved by a nonlinear interaction between the signal and a pump laser within an optical fiber. So in this topic, we are basically concentrate on this EDFA. So it's used to boost the intensity of optical signals being carried through a fiber optic communication system. So in optical communication network, signals travel through fibers for very large distances without significant attenuation. However, when distances become hundreds of kilometers, it becomes necessary to amplify the signal during transit. Optical fiber amplifiers provide inline amplification of optical signals by affecting stimulated emission of photons by rare earth ions implanted in the core of the optical fiber. Erbium E03+ is a preferred rare earth for this purpose. And this EDFA operates in the C band and the L band. So in 1987, Professor David Payne and his team published the research paper of EDFA at the University of Southampton in United Kingdom. So why erbium is used? Erbium has several important properties that make it an excellent choice for an optical amplifier. Erbium ions have quantum levels that allows them to be stimulated to emit in the 1540 nanometer band. Erbium's quantum levels also allow it to be excited by a signal at either 980 nanometer or 1480 nanometer, both of which silica-based fiber can carry without great losses. So in this figure, we can see the typical configuration of EDFA-based communication system. So in this figure, the optical output is first passed through an optical isolator which prevents reflection, that is, allows the light to move from left to right. Here the coupler allows the pump input to be fed into the fiber with minimum loss. So let's talk about this principle of EDFA. Energy level of erbium doped system is shown in the figure. It may be noted that the energy levels from three groups of energy levels marked with their spectroscopic notations. For simplicity, we'll model these three groups E1, E2, and E3 in upper the metastable and ground states. In the absence of any radiation, the ions are in their ground states. If a beam of light of appropriate frequency is incident on the system, the ions will be excited to the higher levels. This radiation called pump radiation. If chosen at 980 nanometer, will excite the ions to the level upper. The lifetime of the ions in the level upper is approximately 1 microsecond. The ions radially decay to the metastable level by non-negative transition, that is by releasing heat. Pump can also work directly at 1480 nanometer to excite the ions directly to the metastable level. In this case, rapid relaxation would occur to the lowest sublevel within the group of levels, metastable, from which laser action would take place. So, the excited ions make transition to the ground state either by spontaneous emission or by stimulated emission. Spontaneously emitted photons bear no phase relationship with one another. It can take place in entire bandwidth of transition and can travel backwards. In stimulated emission, the emission takes place in the wavelength window 1520 to 1560 nanometer if a data signal with the corresponding wavelength is fed into the fiber. We know that population inversion cannot be achieved in a two-level system. However, 1480 nanometer pumping directly to the metastable level can give rise to population inversion because the levels in case of erbium are actually sets of closely spaced levels. So the amplification window of EDFA. EDFA can be used to amplify signal into two bands of wavelengths in the third transmission window. The wavelength range 1525 nanometer to 1565 nanometer is known as the C band or the conventional band, and the second band from 1568 nanometer to 1610 nanometer is known as the L band or the long band. Now let's talk about the pumping methods of ions in EDFA, and those are codirectional pumping, counterdirectional pumping, and bidirectional pumping. So in codirectional pumping, both input signal and pump signal travel in the same direction inside the optical fiber. In counterdirectional pumping, the input signal and the pump signal travel in opposite direction inside the optical fiber. But in bidirectional pumping, two pump lasers are used which travel in both forward and backward direction inside the fiber along with the input signal. Now, gain in EDFA. So, the ratio of the output signal power to input signal power is the gain of an amplifier. It is conventional to specify gain in the logarithmic dB unit, and which is given by 10 log of P out by P in, where P out is the output power and the P in is the input power. Gain of EDFA depends on the pump power as well as in the pump wavelength. The figure shows in below is a typical gain characteristics as a function of wavelength for two different levels of pump power. It may be seen that for small pumping power, the gain spectrum has a maximum at about lambda equals to 665 nanometer. However, as pump power increases, the gain becomes roughly independent of pump wavelength. The gain can be increased by reducing the temperature. Now, gain saturation. From this graph, we can see that when signal power is increased, gain decreases, and when gain is saturated and gain is increased, only noise is increased in relation to signal. SNR increases, where SNR stands for signal noise ratio. Now, noise figure. So what is noise figure? Noise figure is a measure of the quality of amplification. It is defined as a quotient of the signal to the noise ratio of the input signal to that of the output signal. Due to AS, ASE, the output SNR is smaller than that of the input and hence noise figure is greater than 1. That is, an optical amplifier cannot improve the optical signal SNR like gain. NF is also like gain. NF is also measured in logarithmic scale and which is given as 10 log of noise figure. The value of NF depends on the pump frequency. For large SNR values, an approximate expression for NF is given by NF equals to 1 by G into 1 plus 2P ASE divided by H sigma delta, where ASE is the noise power of ASE, sigma is the pump frequency, and delta is the bandwidth of EDFA. And the noise figure thus depends both on the pump power and EDFA length. So in quantum mechanics, it puts a lower limit of 3B to the optical noise figure at higher optical gain. 980 nanometer pumping provides a value of 3.1 dB close to the quantum limit, whereas 1.48 micrometer pumping gives a value of 4.2 dB. 980 nanometer pumping also gives a higher signal gain, the maximum gain coefficient being 11 dB per milliwatt against 6.3 dB per milliwatt for the 1.48 micrometer pumping. The reason for better performance of 980 nanometer pumping over the 1.48 micrometer pumping is related to the fact that the former has a narrower absorption spectrum. So now let's talk about the fields of application. EDFA has the following fields of application. EDFA can be employed in the high capacity and high speed optical communication system. The application of EDFA fiber amplifier is very constructive to deal with the problems of low sensitivity of receivers and short transmission distances owing to a lack of OEO repeater. EDFA can be utilized in long-haul optical communication system. By utilizing EDFA, we can dramatically lower construction costs by increasing the repeater spacing to reduce the quantity of regenerative repeaters. EDFA can be used in the optical fiber subscriber access network system. If the transmission distances are too long, EDFA will function as a line amplifier to compensate for the transmission losses of lines, thus greatly increasing the number of subscribers. EDFA can also be employed in wavelength division multiplexing system, especially dense wavelength division multiplexing system. Utilization of EDFA in WDM system is able to solve the problems of insertion loss and reduce the influences of chromatic dispersion. Now let's talk about the advantages of EDFA. It's commercially available in C-band and L-band. It is a great insensitivity to light polarization state, has very high gain, has low noise figure, is about 4.5 dB to 6 dB. It has no distortion at high bit rates. It can simultaneous amplification of wavelength division multiplex signals. It has immunity to crosstalk among wavelength multiplex channels. It does not require any high-speed electronics, and it's independent of bit rate, as I have already told. As with so many advantages, it also has some drawbacks, like it needs some pump lasers, and it's need to use a gain equalizer for multi-stage amplification. It's very difficult to integrate with other components, and the last one is that dropping channels can give rise to errors in surviving channels. Thank you.